Yes.
How are you doing?
Good. How are you doing? Thank you for letting us talk.
Sure. All right, everyone, these two individuals are going to represent Cupola, and they're going to tell you something about the society. It's an honor society. It's been here for a long time, and if you get involved with it, you won't regret it. That's what I can tell you. All right, take it away.
Hey guys, my name is Caitlin Jenkins. I'm a senior in mechanical engineering.
And I'm Andrew Rose. I'm a junior in electrical engineering.
So does anyone know what Cupola is? Yes, good. We do a lot of volunteering for the school. We basically represent the College of Engineering. When different donors come for tours, we gave a tour of Samuel Ginn, the new Gavin building. We got to be there for the opening. We have kids camps. We really do like just about everything for the College of Engineering, but it's a really great way to get involved, give back to the College of Engineering, and it's a really great group of people too. And it's my favorite part about Auburn.
Yeah, my favorite thing so far about Cupola has been giving high school tours. So like coming out of high school, I had no idea what I wanted to do. Maybe engineering, maybe go to Auburn. And so kind of helping out those high schoolers who are seniors and juniors figure out what they want to do and connect with them has been a good experience.
Yeah, do you have any questions at all?
Let me tell you one other thing. As you start getting closer and closer to graduation, on your resume, honor societies and information like you're involved with Cupola is very important when employers are really getting down to the nitty-gritty and making decisions. If you ever have a chance to get involved with Cupola or invited to Tau Beta Pi, Eta Kappa Nu, or Phi Kappa Phi especially, do it. Because that is something that jumps off the page when you're interviewing. Remember that. For graduate school as well. I think I've taught you.
Yes.
And I don't remember. I taught you 3810 in
This class.
this class. All right. Cupola are the better students. That alone says it. If you're in that society and they see it on a resume, they get thousands of resumes for jobs. They know, especially ex-Auburn people, then they're going to grab that guy or girl.
Mm-hmm.
All right.
Yeah, definitely. I've gotten a lot of interviews just from meeting Cupola alone. So we have info sessions next week, as you can see on this, and applications close January 31st. They're online, and I definitely recommend applying. I've loved every minute of it. So thank you guys so much for your time.
Thank you, everyone.
Thank you guys.
Take care. Oh, boy. I hope there's something to the curtains here. Does anybody know how to open the curtains here? I've never had them closed before on the screen. Oh, I don't want the screen open. Up.
Those ones over there.
What? Go take a look.
There's like a switch on top.
Where do you sit? Where do you look?
Is there like a string or like a rope? No, I don't have an agenda.
Almost everything these days in the auditoriums are done at that panel, except for this, which is on. There you go. All right, does anybody have any questions? Yeah.
The question on 2.18.
All right, listen up, folks. We're going to take care of this. Is this something I'm going to have to look at?
Well, it has X of T going into.
Yeah. He's got two parallel, right?
Mhm.
This is 2.8. Is that right?
2.18.
2.18. 2.18. And they're going to have an X of T here, but then it's going to be broken up. And then some of the signal is fed into, is this H1 or what is this?
H1 and then
H1 of t, and this is H2 of t?
It's H3. There's 4 of them. There's H1 and H2 on top.
Are they all in parallel? Or-
No. They're
What's after this one in series?
H2,
Good.
and then H3 and 4 on the bottom.
And this is a summer, right? Plus, plus, and it's a symbol of summation. And out comes y of t. And that's x of t going to, is that basically what we have, class?
Yeah.
All right, now let me tell you the way this works. When any two functions, if you have this going into this, right? What it's saying is, just follow me on this. If I look at the output right here, just watch this now. That output is going to be x of t convolved with h1 of t. Does everybody see that? Because h1 of t is there. Show, let me see your hands if you see that, right? So it's saying this output right here is x of t times h1 of t. Now that is the input to the second system, right? Do you agree? I mean this system. Which means the output here will be the input, x of t convolved with h1 of t, but then that's convolved with h2 of t. Does everybody agree to that? Input convolved with the impulse response gives me the output. Correct, class? Here's a couple things to take from this, and I mentioned this before. The order of convolution doesn't matter. If you convolve x of t with h2 of t, and then the result convolved with h1 of t, that's valid. Follow me? It's also valid to do x of t times h2 of t convolved with h1, or just convolve h1 of t times h2 of t, and the result convolved with x of t. Got it, everybody? So the order doesn't matter. That's important. And I can prove this. It's in the book. Frankly, I don't want to spend too much time on this. We have some things to cover today. Now, here, it's exactly the same thing. I can just write the output right at this point as x of t here convolved with h3 of t, and that convolved then with h4 of t. I'm glad you asked this. Do you agree with me? Because all these problems make my life easy because they beg the natural question. Right? Everybody see this? Now you methodically can go through and convolve this times that, put it in here, and then convolve this with that, and find the point here where you're going to add to it this. Now, when you're adding two functions, you're just adding this and this. So really your y of t, if you'll notice this for a second, you notice how x of t appears in both the top and bottom? Everybody? Well, you can factor x of t out. And you can say I can take x of t here, and then I'm going to put the convolution symbol right there. It's convolved with this, really. h3 of t convolved with h4 of t plus h1 of t convolved with h2 of t. Follow me? I could factor out this x of t. You all see that, class? Give me a show of hands if you see them. Now that's it. That's the answer. Now they probably gave specific values for h1, h2, h3, and h4, right? We'll do it. If you've worked this problem, this is a good problem because it makes you think and it asks logical questions about, is in fact the commutative property there? Is the associative property there? Can you sum them? Yes, you can do all those things. So can you give me what h1 of t is? I'll put it over here.
It's e to the negative t times u of t
E to the minus t u of t?
minus e to the negative 2t u of t.
Well, how about we do it this way? It's e to the minus t minus e to the minus 2t u of t.
Yep.
All right? For a second, do you know what that looks like, class? This is a double exponential. If you looked at e to the minus t, you would see something that would do this, right? Agree? If I subtract from it e to the minus 2t, well, that function e to the minus 2t, because it's got a negative sign, is actually going down to 0 faster than this one, right? Because you got a 2 multiplier. When you do the math on this minus this, the result is this. This is called double exponential decay. It does this. All right? This is e to the minus t minus e to the minus 2t. And you can find, how would you find the peak value, what the peak value of that function was? Anybody? You know it, I know you do. Maybe you don't want to look like a, you're spotlighting us now. Come on, what do you always do? This is instinct in engineering. If you want to find the peak or minimum of any function, what do? You take a derivative with respect to the variable and set it equal to 0 and solve for the value of t. Correct, class? Once you have that value of t, you stick it back into this equation and find the amplitude. All right, don't ever forget that. That's basic engineering stuff. And that's how you get it. Anyway, I wanted to say that because this double exponential appears a lot. And actually, double exponentials with different constants are used to describe the current in lightning a lot of times. It's called the, there's a rise time and a fall time for lightning curve. I work in that area, so I know this. What's h2 of t?
E to the negative 3t times u of t.
Okay. h4 of t?
E to the negative t u of t.
And I'm sorry, I should have said h3 of t.
That's going to be e to the negative 3t minus e to the negative 2t times u of t.
Okay. All right, when you look at this, this is convolving exponential functions, right? Now, if you're convolving exponentials, really doesn't matter which one you flip or shift, right? In the book, I forgot the page, but if you have your books, you can help me out. There, he has a list of the most common functions that are convolved, and he has 2 exponential functions, and he gives the result. I'll do it one time. Can you tell me where that page is on the book? I'm going to do it over here. I'm just going to show you how to convolve. Boy, I wish I had another board. 2 exponential functions. Let me say the first function is x of t is simply e to the minus at u of t. And the second function, I'll call it h of t, is e to the minus bt u of t. Obviously, each function has the same signature in time. Doesn't matter which ones you flip and shift. Do you agree with me, class? So I'm just going to say this one, x of t, I'm not going to flip or shift. I hope I can do it here. I'll get out of your way. So now versus, it's tau in your book, I graph this one. It's going to be, this is now e to the minus a tau u of tau, but we know it starts at 0, right? And this is tau in this way. That's the first function. That's my x of tau. Next function is this one. I have to flip it and shift it, right? Please listen to me. When I flip it, it would be what? It would be going this way, correct, class? The exponential decay would occur this way. Do you agree when now it's h of minus tau? How many see that? Please show me your hands. Now I'm going to add that t to it, so that will shift it a little bit this way. Are you with me? So now I'm going to have this. I'm going to have e to the minus b times the quantity t minus tau, right? And it's u of t minus tau, but I don't even care about that because this picture tells everything, right? And that's t right there. How many see this right here, what I'm doing? Please let me know. Now you'll notice for t less than 0, there's no region of overlap. How many see that? Can you actually see it in the far back there? Good for you. All right. So that means this is the area of overlap. Now you'll notice that that is for t less than 0, 0. For t greater than 0, there's always going to be overlap. Do you see that? When t goes to infinity, there is still overlap. Understand? But now we're going to do the convolution, and we're going to do it by just point-by-point multiplication. So I take this function times that function. So I have e to the minus a times tau. By the way, e to the minus a times tau right there. And then I'm going to have to multiply it by, now notice I can break out e to the minus bt separately, and then I get e to the plus b tau. All right, so I get e to the plus b tau times e to the minus bt separately. And this is going to be integrated, the tau, from 0 to t. And that would be my y of t for t greater than 0. Greater than or equal to 0, less than or equal to infinity. Do you all see that, class? Show of hands here, how many do? Now you'll notice the e to the minus bt, you don't have to write this down, but I can pull that right in front of the integration. I can just take e to the minus bt out in front because it's not a function of tau, and the integration is with respect to tau. I can also collect the coefficients. This is really e to the what? B minus a tau, isn't it, class?
Yes.
So I'm going to do that too. This is e to the minus, sorry, e to the quantity b minus a tau. And if you want to create a new variable c, let it be equal to b minus a, it's fine. What's the integration of that? Well, this is going to be e to the minus bt here. And then I'm going to get 1 over b minus a here, right? And then I get e to the minus, or b minus a tau, evaluated from 0 to t. So I get really e to the minus, or I'm sorry, plus b minus a t, right here, minus 1. And that's it. Do you agree with me, everyone? Give me a show of hands. Now you'll notice how this actually, whether it's positive or negative, depends on the values of b and a, doesn't it, class? In terms of this number, right? And that is what it looks like. And I'm going to tell you what this does. This actually decays exponentially in time because of this, but this little guy right here will tend to blow it up, and you'll get about this curve right here, what I've just showed you, a similar curve depending on the constants a and b. Everybody see that? Did anybody find the page where the convolution, all these common convolutions are?
57.
57? So on page 57 in your book, they have a list of these. And this is the standard one for if you have e to the a convolved with e to the b. Does he have something like that in the book?
Yeah, e to the AUT involved to e to the BT.
Minus b or plus?
Plus.
All right, I put minuses there. If you want to, this is what I assume that these are minuses. But if he had plus, it's basically you just, all the signs here change. B becomes minus b, a becomes minus a. Follow me in that, class? That's the only thing. Anyway, you can use this one. Now, getting back to this problem, let's take a look at this. Here, what I said, I'm going to convolve these two, right? By the way, what is x of t? Can you tell me what x of t is in this problem? Bless you. Did it give you x of t?
No, it just says the
All right, which means when you do convolutions of these functions, you're going to get a very simple answer. I'm almost positive about that. I don't know what it is. So let's just take a look at this. When I convolve h1 and h2, right? Because I know that's really the thing I need, h1, h2. What is that going to be? Well, h1 is this. Those are two exponentials. h2 is this. Correct, class? Now take a look. When I convolve this with this, what do you get? Here, a is 1, right? And b is 3. Correct, class? So it's going to take a little more time than I really wanted to do it, but let me erase this right here, this portion. That way I have some board. Is the answer for this one provided, by the way?
Yeah, try and prove that's equal to 0.
Well, that's not something to tell you. You know, you might be able to actually get this by looking at it. Let me just take a look at this. Here, let me show you something. I'm going to just try this. If I take a look at h1 convolved with h2, I'm going to omit the argument t. When I look at this, this is really going to be e to the minus t convolved with e to the minus 3t, right? And there's a u of t in all these, but I'm for the sake of trying to figure out the answer, I'm omitting the u of t. Do you all agree with me there, class?
Do you need the negative 2t as well?
Yeah, I'm going to get that. Well, I'll put in the u of t. I have to be on which. I'm going to go ahead and do it. I'm going to take this convolved with this, so I'm going to have e to the minus t u of t convolved with e to the minus 3t u of t. That's the first part. Second part is this times this convolved, so it's going to be minus e to the minus 2t u of t convolved with e to the minus 3t u of t. And then when I look at h2 or h3 convolved with h4, I'm going to get e to the minus t u of t convolved with e to the minus 3t times u of t minus e to the minus 2t u of t convolved with e to the minus t u of t. Y'all agree with that, class? So far? Now, watch the operation here. We have to add the results of these two, correct? You agree with me? Please watch this. These are the kind of problems that come at you, and instinctively you just want to do it with brute force and awkwardness. You want to do all the convolutions and everything, and a lot of the answers will drop out. With problems like this, where there's a lot of different steps, take a step back and see if there might be something that cancels or kills itself. And here, I'm looking at this, since we're adding them up, I see this right here. Well, let's see. Let me just see this for a second.
The first two.
I think, is this the correct H1, H2? Are those correct right there? And H3, H4 and H3 are there? Is that right? They are correct? Because what I expected was this to cancel down here. This is going to be, I don't see that.
Pretty much have to work all to get.
What's that?
I think you have to work all of them to get to 0. I mean, there weren't any that canceled.
Well, there should be. I mean, this one is identical to this one, right?
Yeah.
So you can just multiply one of them by 2 with the addition. Do you agree with me there, class? So if you do that, I'm going to go ahead and do this. I'm just going to say I'll get rid of this, since we're adding these two anyway, and put a factor of 2 there, right? Now when you do the convolution of those two things, it's 1 and 3. And you have 1 and 3, let A be 1, B be 3, that's going to be a half. I think you're right. You're going to have to work them, but you're going to find out, because you're really subtracting the exponents, and like here you're subtracting them. You're going to ultimately find out that that whole thing equals 0. Did anybody work through the steps on this at all? It does come out right, doesn't it?
Yeah.
I'm sorry, I thought there'd be a quick cancellation here, but no, honestly, I don't see it, but you're gonna have to work it. But we worked it for the general case. I mean, this is a general case, right? Any two exponentials. The only thing you have to do is fill in the constant values there. Okay, class? That's how you do that problem. I really don't want to spend too much time on one problem like this. Is there other questions? I hope I answered. Who asked this? You did?
Yeah.
Does that make sense? But that's the trick. Get it down to a final form. I thought we'd be able to cancel a few. We just got a fact. We got 2 there. We got rid of one effect. Go ahead. What else? Anybody? About the homework? Yeah.
This part beyond homework 3 is an exponential and a square or UT function being complemented together.
All right. We'll do that one. That one's not too bad. At least I don't think it's too bad. I hope you realize that a lot of these things take time. This is one of the few topics I dedicate 2 lectures to. I mean, this is just continuous time convolution. Most, you only get 1 lecture. All right, for this problem, this is problem 3.
Yeah, it's homework 3, part B.
Homework 3, part B. Go ahead.
First graph. It starts at 1, goes up to 1.
Wait. Help me out here. Is it an exponential decay? Or
Yes,
what?
sir. It's exponential decay.
It starts at 1, it's equals 0?
No, it starts at time equal to 1. And
Oh, at 1 second.
Yes,
All right,
sir.
so it's delayed.
Right.
And then it exponentially decays?
Yes, sir.
Well, this is the one we were talking about. Yeah. Like so?
Yes, sir.
And this is x of t?
Yes.
And what about the other function?
It's just u of t starting at time equal to -1.
That's a good problem. This is -1, this is u of t, right?
Yes, sir. Or u
Yeah.
of t plus 1.
Yeah, u of t plus 1. Correct, class? Now, with this, The one that has the most going on, in my opinion, is the x of t. So I'm gonna leave that alone. I just draw that versus tau, and I go ahead and do that. So here, and this is going to be e to the minus, is it have an equation for this?
It
Is
has
that-
an equation, it's, e to the minus t minus 1. Times
u of t minus 1?
Yes, sir.
Okay, that's it. Now the next function here, pay attention to this, class. When I flip, right? I'm not going to shift it, I'm just going to flip it. Follow me, class? When I flip it, I get this. And this would be u of simply minus tau, or I mean minus tau plus 1. Wouldn't it, class? Follow me? I just simply changed the sign of the horizontal variable. Now, what do you notice at that point? You notice if whenever I add, I mean this function right here, what I'm going to do is add t inside here. Eventually, I'm going to say plus t, and t is going to have values, right? But when t is 0, this is what I have, don't I? You'll notice it's just about to overlap. So for positive t, what happens is what? Now this is going to move, right? And this point here, and I'm going to go ahead and do it now. I'll add the t here, minus tau plus 1 plus t. And now I can say this is going to move just a bit. And this point right here will be t plus 1. Because at 0, when t was 0, it was 1. Do you follow me, class? Show of hands here. You got it? Now, what's the area of overlap? It is from 1 to t plus 1. How many see that? Y'all, this is a good problem. It makes you think. Forces you to think. You got a reason. So now when I look at the output, now first of all, for t less than 0, does everybody agree that there's no overlap? And therefore the y of t, the convolution of those two is 0. Does everybody get it? Mm-hmm. But for t greater than 0, the area of overlap would be from an integration from 1, right, because that's at 0, to t plus 1. So now we take a look at this, and we're going to take, since this is just 1 here, that has a height of 1, we're going to take the integral of e to the minus quantity t times e to the 1. I'm going to go ahead and separate these, so I have e to the minus t times e to the 1. And then it's going to be times 1 d tau, the integral from 1 to t plus 1. And that would be my y of t for t greater than or equal to 0. Do you all agree with that? Take a look at that. Everybody agree with that? I simply took the value of this function, I separated these two things out, right? And actually that should be tau, I'm sorry. This is tau, right? My bad. You have to, it's a variable is tau. I should have put it in there. Now when you look at this and separate it, guys yell at me when I do something wrong. I'm on camera, I don't want it too bad. Are you all with me on this? I mean, it should be a function of tau. I do these so often. I actually use other variables. But are you with me on this one, class? Now, if you do the integration, what are you going to get? You're going to get minus 1 over tau, right? Times e to the 1, right? And then it's going to be times e to the minus tau evaluated from 1 to t plus 1. Or, and I'm just going to give you a tip on this. You notice there's a minus sign there, because when we integrate it, we get 1 over minus tau, right? Now watch and listen. Whenever I see a minus sign, this is just my way of doing business. Instead of dealing with a minus sign and evaluating this at the upper limit minus this, what I do is make this a plus, and I take this limit, I put it down here, so it's 1 plus t, and I take that limit and I put it here, and that gets rid of that negative sign. Everybody understand that? If you switch the limits, you switch the sign out in front. How many know that? All right. It's a smart thing to do. It saves time, usually, and confusion. So if I see a minus sign here, I get rid of it, and I take that limit, put it here, this limit here. Yes, sir.
Why is there a 1 over tau?
Well, if you integrate e to the at dt, don't you get 1 over a e to the at evaluated over the upper? It's 1 over a, right? A here's, I'm sorry. Sorry, I'm sorry about that. Today has been one of them days. You are right. That is my bad.
I made the same mistake when I was.
No, I have had a horrendous morning. So I'm still regrouping. Sorry. I didn't even get much of a lunch. Are you okay with that, class? You're right. Thank you very much. Any other mistakes that I made? That's the way you do it. And I just switched the limits, by the way. The minus sign would still be there. Yes?
For the boundary condition, why do you do it from 0 and not 1? Because there's nothing overlapping between 0 and 1.
No, I integrate, look, at t, remember, we're integrating with respect to tau, right? Oh, I know what you're getting at. You're saying, what is tau here? It's 1. What is tau here? It's t plus 1. Those are the limits of tau. See, you're integrating with respect to tau. Well, what do you start at? You start at 1, don't you? And you go all the way up to t plus 1. But you don't go at 0, right? Because there's no overlap on that function at 0. It's a little confusing at times. How many see this right here? And I apologize for messing up that in. So if you do this, what do you get? Well, I get e to the 1 for starters, and then if I evaluate these things correctly, hopefully, now I get e to the minus 1, right? Minus e to the minus quantity t plus 1. Do you agree with that, class? And that, is that the answer he has, or a form like that? You can multiply them through. This is just going to be 1 e to the 1 times. Minus 1 is just 1, right? Correct, class? And then you get this one, you could get e to the 1 times that. It gets rid of the 1, it's just 1 minus, so the answer would be 1 minus e to the minus t. Is that what he has? Yep. All right, are you with me? And that's it. That's a good problem. Any other questions about the homework? These are meant to challenge you. Yeah? Did you have one? No? All right. All right, so we've covered convolution. You've got several different finite value functions. You got several different functions that were exponentially decaying versus convolved with like a u of t, or 2 exponentials convolved, both of which start at 0. And you had you also had a triangle function convolution with a square. And we could keep going on and on. There's a million permutations. I could have like a t squared times u of t convolved with an e to the minus at u of t. That would be integration by parts. But you can go through all the permutations, but you do have to know how to do them. And unlike today, what I did, make sure you come in rested and sharp for these kind of quizzes on Friday. There'll probably 3 different quizzes here, 2 or 3 different quizzes, and each person will get a different one, so your neighbors won't be able to copy off them. And and also I'll make everybody get up and make sure there's nothing on your seats. Take your cell phone, turn it over, and shut it off on the desk during the quiz. The other thing I'm going to tell you, my graduate assistant will be in here too, and he'll probably be walking up and down the aisles during that. Try to give yourself as much space as possible for the quiz on Friday, and try, if possible, to put at least 1 desk between you and your neighbor, all right? I'm trying to give you the heads up on this. Now, do you have any more questions about continuous time convolution? Any? All right. And this is just my opinion, but it in my opinion, is the most difficult concept you've been up against yet. I don't know if that's true for everyone. And some people, it's my understanding, have actually done this in the differential equations course, and not because the instructor covered it, but because they were interested. But there's almost nobody that runs into this stuff until here in this course. Yes, sir.
For the quiz and just in general, are you going to ask us to do it graphically or analytically, or is it up to us?
I may give you a function, I may give you a graph. The answer is going to be, you're going to provide a sketch, and usually for the regimes, if there's 3 different regimes of time, then what you're going to have for t less than 0, you'll put down where they are. I'll give you like 3 slots, and tell me what the output is of convolutions of 2 functions. I'm not going to ask you to convolve 3. I'm just like, and they're simple. If you've done the homework and you understand homework, people usually make near perfects on my quiz or perfects. If you don't understand the homework or you're unsure about things, then there's a lot of people that make 5 or less, sometimes zeros. So I'm just telling you, there's a huge spread in the grades here. There's a lot of people with 0s to 3, and a whole bunch 9s and 10s. So that's what I've always seen. There's not much in the middle. All right, now today what we're going to talk about is discrete time convolution. And let me tell you something. This is actually a little more important than continuous time because all the systems in today's world are digital. They are things that act at given set points from sampling, and they have discrete values. So this is a more important concept, but it's the same concept. And I always cover continuous time first. So if you have functions that are digital, or I should say, that are for discrete time, the values are going to be n equals 1, 2, and 3, and 4 instead of t. Instead of t, we have values of n. That's your variable in time. Instead of x of t, you will have x of n. There's usually square brackets there, not parentheses. To me, I don't care. When I see an n, that tells me it's discrete. Next, there's differences in the functional form. So listen. In continuous time, you had a delta t function. That went to infinity at t equals 0, or when the delta function came on, and it had an infinitesimally small width, but the product of the width times height was 1, right? Well, here in discrete time, we have a delta n, but it's defined as 1 for n equals 0 and 0 else. What it really means is, now, that's almost like defining the area under a delta function, but it's 1. It is not 0. It's 1 when n is 0, and it's not infinity for discrete time. And then for all other values of n, it's 0. So that's the difference. Now I could go ahead and say, well, if you take, here, how did we get u of t? From delta t. Didn't we just integrate delta of t prime dt prime from minus infinity to t to get u of t? Didn't we, class? How many remember that? We did the integration. Well, now, if we're in discrete time, we don't do an integration, we do a summation. Follow me? Discrete would be sum. So now over here, your u of n would be equal to the summation, you're not going to like this, of delta of I, where I goes from minus infinity to n. Now just think about it for a second. This is that, I hate to put square brackets, but I'm just not good at drawing square things. I tend to write too fast. Now if you look at that, think about this for a second with me. If I sum up and n is less than 0, got me? If I go from minus infinity, say minus 10, minus 11, whenever I evaluate anything but n equals, this is I, not n, I. Gosh. Whenever I evaluate anything in here that is not 0, it is 0 still. Understand? So until this value n is 0 or greater than 0, this is 0. Follow me? But every time n is greater than 0, that one time when I'm summing through 0, I get 1. And so therefore u of n is equal to 1 for n greater than or equal to 0, and it's 0 for n less than 0. That's u of n. See the parallels? And if you really want to know the truth, what that's done is sampled u of t at the value t equals 0, 1, 2, 3, 4, and just place that value as a point on a plot. With me? Felt it. We can keep on going on. You could say there's equivalent to a ramp function. I don't think your book does this, but I could say if I have n u of n, that would be a ramp function sample, wouldn't it, class? It's just going up at a rate with a slope of 1. Understand, class? So these are the discrete, and there really aren't any difference with the functions like sine, cosine, stuff like this. Perhaps there's one function that's not defined. I don't think it's defined well in your book, but it is used. Over here we have a function called pulse of t, p tau of t, which is rect of t over tau. And remember what that looked like. It was just 1, right, from tau over 2 to minus tau over 2, right? The spread of that was 1. This is p tau of t, right? Now, there is, in some books, also a function that's like this, but I don't think our book has it. And it's simply p, and then the subscript here has a meaning. The subscript is 2q, now of n. What that means is whatever that number is, say the number was 8, the value of q would be 4. Understand that, class? 2 times q would be whatever number is the subscript. But the number of points that are non-zero will always be odd because they're 0. So let me just show you. If I say I've got this, what this looks like is a function. This one isn't that important to understand, but I need to show you. What it looks like a function, if this is 0, 1, 2, and let's just say 3 here, minus 1, minus 2, minus 3, and I'm going to go ahead and say this is 2q will be equal to 6. Are you with me? I'm just picking a number out. So if 2q is equal to 6, then q would be equal to 3. 6 would be the subscript there. With me, class? This goes all the way up to the value of q and down to the value of minus q, and its value is going to be 1 at all integer values between minus q and q, but after that, 4, 5, 6, minus 4, minus 5, and so forth, or 0. So it's really like a pulse function, right? A regular pulse. And we're sampling it at all the points that are discrete, or that really integer values. And you have to include 0, remember that. So it's always an odd number. Always an odd number. Understand, class? How many understand? That's a pulse function that's used. Now, when you do continuous time convolution, you use these relatively new functions plus any old functions. Sines, cosines, exponential decay. You can have a to the n, anything like this. I'm going to do a few for you and show you. Suppose I want to convolve two functions, and I'll actually do it. I was thought about not doing it, but I'm going to do it. Let me just show you discrete time convolution the same way I did continuous time convolution. Suppose I have a system, and this time it is a discrete time system. So instead of having an h of t, now it's going to have an h of n. H of n is the impulse response in discrete time. Understand? Not continuous time. So if I have a delta of n coming in here, my output will be an h of n. Got it, everyone? Now, if I go ahead and I say I shift it a little, I'll draw this one here. Now if I go ahead and shift it, and this is still, the system is defined by what's in this box. It's h of n would be called the impulse response of the system, discrete time impulse response. With me? Now if I go ahead and I say my input, I'm going to stagger it. I'm going to put delta of n minus I. All right? What's my output going to be? Right, h of n minus I. Very good. You're going to, some of you people have picked up on exactly where I'm going with this. Anybody want to take a shot at what the next step is? You probably do. What did I do next time? Did I multiply this guy by a constant, right? Do you remember that constant was x of t, or x of tau, right? Well, now it's not going to be that. It's going to be x of I. Very good. You see this. And that means this is going to be multiplied by x of I. Correct? X. Remember, n is the thing that's varying, really. I isn't. Follow me? That's like a constant, x of I. Everybody with me, class? Keep watching. What's my next step? I know some of you know this. There's some very bright people in here. There's also people who are reading ahead. There's people that they don't want to say anything. My wife is that way. She, for the life, she will never, ever in a crowd say a word that would bring attention to her. Shy than anything. When she's at home, she's threatening. Oh God, that's on tape. I retract that statement. So if you come here The next thing I'm going to say is, what do you think I'm going to do? Before we integrate it, right? What do you think we're going to do? Sum, right? And what happens if you sum this, right? For I equals minus infinity to plus infinity, I would sum this as well. Let me break that out a little. I would have x of I, h of n minus I, and now I'd sum this, and it'd be from I equals minus infinity to plus infinity, right? Let's talk about this for a second. When does this delta function have a non-zero value? When this argument is equal to 0. When is n minus I equal to 0? When I equals n, right? And therefore, what is it going to do? Extract the value of x of n. Follow me? Do you agree with me? All right, now what about over here? Well, now this is y of n. That is now the response to the x of n, right? How many see this? If you don't, spend some time thinking about it with some coffee or tea, and it'll come to you. If you're meant to be here, it'll come to you. You got it, class? And this is convolution in discrete time. It's similar to continuous time. It's identical as far as the steps we do in continuous time to get to the answer, except there's not an integration, it's a summation. You all see that, guys? And this is done. I do the continuous time one first because it's much easier to see, in my opinion. You're used to seeing exponential decays and sine waves and things like that. You're not used to seeing dots. They just go down to start having different properties or different trends. So this is the definition of convolution of any two signals. And I'll put it over here. And then we'll do some problems. I can show you some tricks too to this one. You're going to like this. They're not in the book. And I mean, the guy that wrote the book, Willoughby, is a real bright guy. But I don't know what in the world he was thinking omitting this. Listen, when I teach a class, what I like to do is tell you everything I've learned, all the tricks, all the things that can really make your life easy, how to see through a problem. I've had professors that will never do that. I don't know why. They're paid to teach. And to me, that's the best way to teach, is tell from your experience how the easiest way to go about getting the answer. So I'm going to try to give you some insight to this. If we're going to do any kind of convolution, a discrete time convolution, it's really a summation. And in general, the convolution of any two functions, call it x of n, convolved with h of n. That's the same thing as h of n convolved with x of n, right? And that's equal to the summation here of I goes from minus infinity to plus infinity. You're summing over I of x of I times h of n minus I. And by the way, it can be h of I times x of n minus I. Doesn't matter which function is first. Got me on this, everyone? Now, when I have that, what's really going on? Well, this I is like tau, right? Y'all agree with that? Very similar to it. It's a dummy variable that gets integrated out. This n minus I is like t minus tau. We're going to integrate in tau, but the t is the thing that comes out of it and remains that we care about, right, class? So if you have two functions and you do the same thing graphically as you did before, find the one that's got the most crazy stuff going on and use that as your first function where you're going to plot it versus tau or versus I. Your second function is the one you flip and shift. All right? But now it's going to be with discrete values. Let me give you I want to do a problem or two for you so you'll see this. I'm going to choose a function. I'm going to say my x of n here is going to be a to the n u of n. I'm going to stipulate something. I'm going to say the magnitude of a is less than 1. I want to do this so this thing's going to actually asymptotically go to 0, not blow up to infinity. With me? Now, the second thing I'm going to do, the u of n means it's 0 for n less than 0. My second function, my h of n, I'm going to make it the easiest possible function. Well, maybe not the easiest possible, an easy function. I'm just going to let it be u of n. With me? Now, of those two, it's pretty easy. Which one has the most going on, changes the most? Excellent. So now you take that and you plot it versus I. It's straightforward. Come over here. Here's I. 0, 1, 2, 3, and so forth. And I have a to the n. Well, when n is 0, anything to the 0 power is 1, right, guys? And u of 0 is 1 as well. So it starts at 1, which is nice. Now, if a was greater than 1, it would start blowing up. But a is less than 1. I've constrained it. So it's going to look, now it's not going to look like that. It's going to look like these points. Follow me? There's a point, there's a point, there's a point. That's, let's see, 3, 4, 5, and so forth. And this is versus I. And that's my x of I. Got it? Now below here.
That includes when I is 0.
Yeah. Sure. Because in I is 0, it's 1, isn't it? Go ahead and just take a look at this. If I, you remember you take n and replace it with I. What is u of 0? 1. Right? It's 1. And what is anything to the 0 power? 5 to the 0 power is 1. Understand? It's just a definition, mathematical definition. Now we take this function, u of n. You know u of n looks like this if we plot it versus n. Plot u of minus I first. It looks like this, doesn't it, as far as the envelope, class? And then when I add n to it, now notice I'm going to do this all in one fell swoop. I'm going to say this is u of I minus n. For this one, I let it land at 1, just so you can see it. This would be n equal 1. You all see this, class? And it's not going to have this, it's going to have these values. There's 1 here, 1 here, 1 here, 1 here, 1 here, but this is the envelope. All these values are 1, and it looks like a curtain being drawn in this direction as what? As n increases. Doesn't it, class? How many see this right here? Same exact principle as the u of t, isn't it? Only at discrete values. Now when I take a look at this, depending on the value of n, first, do we all agree for n less than 0, there's no overlap of these two? How many agree with me there? Because what? If n is less than 0, this curtain, or this envelope, is now starting back here, right? And if you look straight up, there's 0 here, and if this one is being multiplied by 0 down there. Correct, class? So that means we know the actual overlap point, where the two functions, point by point multiplication, are going to be non-zero, starts when n is 0. And when n equals 0, for n equals 0, you'll notice we get 1 times 1. Your output is 1. Correct, class? Just by inspection. Now, the next point, if n is equal to 1, now you would get 1 times 1, or 1 plus 1 times a to the 1, right? Or plus a, or you get 1 plus a. Follow me, guys? Now, if n is 2, you would get 1 plus a squared. Y'all see this? And you can allow the permutations to go on and see how it extends. I'm going to write down what y of n is. And I think you can all see as this is going, you're just adding one more term. This is a squared, this is a cubed, a to the 4th, and so forth. Do you agree with me? So now I can say that my value y of n for the convolution of those two is really a summation where I goes from 0 to n of a of n. A of I. Gosh. I'm in a careless. That's what happens when you don't drink coffee. I'm used to a few cups in the morning. But you all agree with me there, class? What is that value? I've got to show you a trick on this. This is a G. Yes, sir.
I just want to say, your bottom function, you have I minus n. Shouldn't that be n minus I?
You're absolutely right. You're absolutely right. Thank you. It's too late. I'm sorry, I'm over. Yell at me if I'm going. If it's fine. When it's over, just let me know. I'll get to this. I wanted to finish this thing up, but I got to show you some tricks. Sorry, guys. Yell at me if I'm going over. I don't pay attention to my watch when I don't have it.
I was trying not to be
What's that? No. I was scared, but I think I can do it. Yeah, step one. Let's do this and what? What about today? Pain.